This is Hardware AI for Group B02. So our neural network design is a simple convolutional neural network where we have the first convolutional layer with a ReLU activation, then max pooling, followed by the second convolutional layer with a ReLU activation, then average pooling, then finally a fully connected layer with output of 5 values corresponding to 5 labels. Mathematically, the functions are as follows and can be implemented in C++ HLS code in the next few slides. The convolution is a quadruple for loop with the comments detailing what each loop represents. Pooling simply combines values within each channel in a certain way. Max pooling is to max over values and average pooling is to average over values. ReLU forces all values out of convolutional layers to be non-negative and is a simple check against 0 as seen in the code here. The fully connected layer is just a matrix multiplication implemented as a for loop. The all loops can later be optimized using the Pragma HLS tools. Here we have the overall network making use of the functions shown in the previous slides. After exporting from Vivado HLS, we can import the IP into Vivado using a simple two-step procedure. First, you go to the IP catalog, you add a repository, then you create a block design, and you add the IP block. The input-output interface to our CNN IP makes use of the XC DMA as shown below. So we have the out of the CNN connected to S-axis S2mm, and the in of the CNN connected to M-axis MM2S. This is the overall block diagram where we also have a BRAM controller and block memory generator. This is to handle large amounts of data going to the CNN IP. Program the FPGA is made easy using the PINC library, where after transferring the generated bitstream to the Ultra 96, we can access the DMA send and receive channels as shown. To test that the IP core is working, a test bench is set up in HLS. C simulation and RTL co-simulation will verify that the IP works as expected. If we compare with the expected output and we have a difference, the test will have failed, where we can modify our implementation to make sure it is correct. Segmentation of the signals involves windows of 30 samples, which is equivalent to 1.5 seconds of data at 20 Hz. Each window is collected at 10 sample steps, where features are extracted from the window to be used as inputs to the neural network. Feature extraction involves working on subsignals within each window. The values of features from each subsignal are collected into sequential data, 15 to be exact for each feature, as seen 2 slides ago. LGBM classifier is used in software to determine the importance of each feature, contributing to being able to classify the signals better, where less important features are dropped and not chosen for the final neural network model. Training the neural network involves making sure we have a train validation test split, an optimizer, and a loss function. Here the train validation test split is 50, 25, and 25%. A model validation and tuning of hyperparameters is done using performance on the validation set. We have hyperparameter tuning to optimize the performance of the model given our data. Some of them are included on this slide with some of the explanations given on the slide as well. By a rough test, a good learning rate is actually 0.1 and a good number of epochs seem to be 50, but this might change given more data, given more tuning, right? There's also the architecture. There was testing of different architecture with even more complex and more layers, and the chosen dataset seemed to work best given the current resources. The confusion matrix is obtained as such, with the hardware performance being similar since both are using 32-bit floats. The accuracy is around 86% in this case, but it could possibly be improved. Feature extraction makes use of the following Python libraries. Of note are the entropy for signal entropy in the frequency domain and the LGBM classifier for quick high performance classification. PyTorch is also used to build the neural network in software. For start of move identification, this involves looking at the minimum to maximum raw values of the raw signals before we extract out the features, where we filter out those that don't meet a certain threshold, seen in the next slide. The range of minimum maximum values on the gyroscope for actions are much larger. For example, we have GX values on average ranging from -27 to 32 for actions, while it's just -9 to 11 for non-actions. We can filter signals that have a minimum below -20 and a maximum above 20 before sending it to the neural network. Hardware optimizations can also be made in HLS code, where three main types of pragmas are used. The main ideas of each pragma are listed on this slide and are implemented into the functions seen at the start of this presentation. This can be seen in the bottom right of this slide. The optimization actually vastly improves latency by almost over 20 times looking at the synthesis results. Area also, while increased, is still at a reasonable level. Last but not least, we have power optimization on the Ultra 96. PM bus is used to obtain the power usage. And then we have before and after values compared, where shutting down CPUs using the command as shown on this slide does make a difference. The next few slides will showcase some video demos of what we've talked about earlier. So on this slide we have the Vivado IP setup. After we export from HLS, we can easily import it into Vivado using the import IP, and we have it in our block design. There's also some of the other things I talked about, like the ports and the other blocks we used in the block design. This video shows the ping sending and receive to the FPGA actually running and getting an output. Over here we send an array of size x.shape here, and the output buffer is the classification label, which is 4. Here we have the RTL co-simulation, which actually passed because yeah, the expected output is correct. So here we have the neural network training, where we actually train the data on the training set and then subsequently validate the data on the validation set. As you can see here, we have the learning rate as a hyperparameter, as well as the number of epochs. They were actually tuned as mentioned in the earlier slide. So they were tuned with reference to the validation set. And that's pretty much all I have for this presentation. Thank you.